In our first video, we had a good look at Bayes' theorem. If you haven't seen the video, I suggest you do, otherwise you probably won't follow much of what I say in this video. If you've done it, you know that the Bayes' theorem can be written like this, where PP is the posterior probability, that is the probability of the hypothesis in the light of the evidence. TPR is the true positive rate, i.e. the probability of the evidence if the hypothesis is true. FPR is the false positive rate, the probability of the evidence if the hypothesis is false. And BR is the base rate or prior probability of the hypothesis. In odds form, the theorem can be written like this, where PO are the posterior odds, BO are the prior odds or base odds, and the ratio of the true positive rate over the false positive rate is called the likelihood ratio. You also know the relationship among the four terms in this 2x2 matrix, where by definition the false negative rate equals 1 minus the true positive rate, the true negative rate equals 1 minus the false positive rate, and symmetry is defined as a situation where the two error rates happen to be equal, and therefore the two true rates are equal as well. And therefore, not only the rows but also the columns of this matrix add up to 100%. We concluded the video by introducing the concept of prior indifference. Between the two extremes of faith, where the base rate is either 1 or 0, prior indifference is base rate equals 1/2. Whereas with faith we are absolutely sure that the hypothesis is true, or absolutely sure that it is not, that is false, irrespective of any evidence, prior indifference means that we have absolutely no idea whether the hypothesis is true or false. Under prior indifference, Bayes' theorem simplifies to this, which says that the posterior probability equals the true positive rate divided by the sum of the true positive rate and the false positive rate. In odds form, it simplifies to this, which simply says that the prior odds, or the posterior odds, are equal to the likelihood ratio, given that the prior odds equal 1. Since typically the two error rates are quite similar, and therefore the denominator here is not very different from 1, we can say that under prior indifference the posterior probability is close to the true positive rate. And under symmetry, which remember means that the two error rates are equal, the posterior probability equals the true positive rate exactly. So, under prior indifference, we have that the probability of the hypothesis given the evidence is close, and under symmetry exactly equal to, the probability of the evidence given the hypothesis. We call this the inverse fallacy, but forget about it for the moment and let's go back to the Bayes' theorem. As you know by now, the posterior probability depends on three things: TPR, FPR, and BR. And under symmetry on just two things, TPR and BR. This is a Bayes' theorem under symmetry, which you get if you replace FPR here with 1 minus TPR. To use Bayes' theorem, you need a hypothesis and some evidence associated with it. Once you have these, you need to come up with TPR, which again is the probability of the evidence, given that the hypothesis is true, FPR, the probability of the evidence if the hypothesis is false, and BR, the base rate or prior probability. In the first video, we saw the hypothesis of fire and the evidence of smoke. In the blog, I've used lots of other examples. I've discussed the two examples in Nate Silver's book, The Signal and the Noise. The hypothesis of a terrorist attack, given the evidence of two planes hitting the Twin Towers, and the hypothesis of infidelity, given the evidence of an unfamiliar piece of underwear found in a drawer, an example which I then developed into a looking at Othello and Iago's trick to mislead him. I then used drug tests, weather forecasts, and expert predictions. I've used Kahneman and Tversky's CAB problem and Linda's problem. And in the blinded by evidence paper, I have used the hypothesis of a virus infection and the evidence of a test result. But the original example I came up with is that of a child footballer. Imagine you're a parent watching your child playing football. You think he's very good at it, but being a parent, you know, your judgment may be highly biased. So, in order to have an impartial opinion, you ask the coach. He suggests that the child take a test. The test has been used for a long time and it has never failed to detect a champion. That means all children who subsequently developed into football champions, with no exception, scored very highly in the test. Interesting, you say, but wait a minute. What if the child scores highly but then fails to develop into a champion? That can happen, says the coach, but not often. Only 5% of ordinary children get a high score. Oh, well, let's go for it then, you say. The child runs the test and he gets a very high score. So here's the question. What is the probability that the child will become a football champion? Don't worry about giving a number. Just think about whether the probability is high, middle, or low. You should also not worry about whether to trust the data. Just assume they are correct. The test is that accurate. In fact, the coach might have simply said something like, look, I've been a coach for over 40 years, so I have a long experience. I'm telling you, when I see a champion, I'm never wrong. And then he gives you a long list of famous champions. All of them, I said they would be champions, and they did. No exception. So I'm an infallible champion spotter. I never miss one. Now, I'm not perfect. Sometimes children who I thought would become champions, in fact, didn't. But even then, I have been very accurate. For every 100 ordinary children, I wrongly called champions only 5 of them. But I'm telling you, I think your child is a true star. So there, what do you think? If you're like most people, and if you have not read my blog, you think the probability is high, actually very high, between 95 and 100%. Your thinking is something like, I don't know whether my child is a champion or not, but the coach says he is, and the coach is very accurate. In fact, he's infallible at spotting champions, and only rarely mistakes an ordinary child for a champion. If that's the case, then the probability that my child is a champion must be high. Let's see. What we are after is the probability that the child is a champion given that the coach, or his test, says he is. What we know is the true positive rate, the probability that the coach says the child is a champion, given that he is. That is 100%, which is the same as saying that the false negative rate, the probability that the coach says the child is not a champion, given that he is 0%. Remember, the coach is infallible at spotting champions. And we also know the false positive rate, which is the probability that the coach says the child is a champion, given that he isn't. That is 5%, which is the same as saying that the true negative rate, the probability that the coach says the child is not a champion, given that he actually is not a champion, is 95%. Notice that of the two possible errors, false positives and false negatives, it is the latter that you really want to minimize and, if possible, entirely avoid. That's the case where the coach says the child is ordinary, while in fact he is a champion. Make that error, and you've thrown away the golden chance to be the proud father of a football star. There is little doubt that this would be much worse than a false positive error, where the coach says the child is a champion while the child turns out to be ordinary. That would be disappointing for sure, but not as much as a false negative. With a false positive, there is much less regret. At least you give it a try. That's what makes the coach's prediction in this case particularly enticing. It is what I call a barking dog, conclusive evidence, no false negatives. On top of that, there is only a small false positive rate. The coach is really very accurate. And remember, we are assuming that his accuracy is for real. But wait a minute. We said we need three things to calculate the posterior probability. We know TPR and FPR. But what about the base rate? By concluding that the probability that the child is a champion must be high as a result of the coach's prediction, it just so happened that you forgot all about the base rate. Worse, you didn't feel any need to know it. Why? Let's rewind. You look at your child and you ask the coach. But now imagine that the coach does not offer any test or opinion. He just says, look, who knows? Your child looks like a good player, but the fact is, football stars are very rare. There are thousands and thousands of children playing football, and only very few become champions. For a child like yours, I would say the chance is 1 in 1,000. Such a prudent assessment would sound about right and feel quite obvious. But the crucial point is that the moment the coach made his forecast, such an obvious, correct and sobering reality ended up having no influence on your probability assessment. After the coach's accurate forecast, your probability was high, irrespective of how low it would have been without the forecast. This is a huge mistake. You have to have a base rate to start from. Let's assume the base rate is 1 in 1,000, as the uncommitted coach suggested. You plug that into the Bayes formula, along with the 100% TPR and a 5% FPR, and the result is that the probability that your child is a football star after the coach's forecast is just about 2%. So very low, and much, much lower than what you thought. What happened? It is that by disregarding the base rate, you were prior indifferent. You implicitly assumed BR equals 1/2. When you do that, you can see BR disappears from this formula. And what you're left with is this, which equals 95%, about what you thought it was. That's why this is called the inverse fallacy. It's because it amounts to confusing the probability of the hypothesis given the evidence with its inverse, the probability of the evidence given the hypothesis. It goes under many other names: invalid inversion, error of the transposed conditional, prosecutor or juror fallacy, base rate fallacy or base rate neglect. I prefer to call it prior indifference fallacy because that is what it ultimately is. The base rate is not neglected per se. It is actually visible and obvious until the evidence arrives, in our example in the form of the coach's forecast. It is at that point that the base rate disappears from our sight, because, as I say, we are blinded by evidence. It is like with optical illusions. Prior indifference persists despite our full attention. It is there not because we ignore evidence, but because we are blinded by it. Notice that the coach's prediction is highly valuable. It helps to turn a 0.1% base rate into a 2% posterior probability, a 20-fold increase. The evidence is highly confirmative, but definitely not as confirmative as it looks under prior indifference. So here's the paradox. You requested the coach's opinion because you wanted to get closer to the truth, but in fact, you ended up straying far away from it. A look at the corresponding 2x2 matrix can help us see what is going on. To have big nice numbers, let's make the unreasonable assumption that the coach has seen 20,000 children like yours. Of course, nothing changes with a smaller number. We see here that the base rate is 0.1%, 20 over 20,000. Here we see there is no false negatives. The false negative rate is 0, and the true positive rate is 100%. And here we see the 5% false positive rate, 999 over 19,980. But despite low error rates, we see that while the coach made 20 correct predictions when the child was a star, as many as he could have made, remember, he got them all right, he made many more incorrect predictions, 999, when the child was not a star. True, these are only 5% of all non-stars, but the crucial point is that they are 98% of his star predictions, 999 over a total of 1019. In other words, he made only 20 over 1019 correct star predictions, which is exactly the 2% posterior probability according to the Bayes theorem. Here is another way to see it. To visualize it graphically, let's make a slight change and assume symmetric evidence. So instead of taking a 0% false negative rate and a 5% false positive rate, let's assume they are equal, thus reducing the inputs into the Bayes formula from 3 to 2, and therefore allowing us to picture what is going on in this graph. This is the relationship between the true positive rate, which remember under symmetry is also the true negative rate, and the posterior probability. It is obviously a positive relationship. The higher the TPR, the higher the posterior probability. But it's not linear, except when the base rate is 50%, i.e. under prior indifference. In that case, as we know, PP equals TPR, giving a 45-degree line. But if the base rate is lower than 50%, the relationship becomes convex, and increasingly so as BR tends to 0. And if the base rate is higher than 50%, the relationship becomes concave, and increasingly so as the base rate tends to 1. Here we have drawn the lines with BR equals 1% and 99%. You can see that with perfect evidence, that is TPR equals 1 and or TPR equals 0, PP is also 1 or 0. But you can also see that even a slight drop from 1 can cause a large drop of the posterior probability if the base rate is small, as in here. And even a small increase from 0 can cause a large increase in the posterior probability if the base rate is large. Prior indifference, therefore, is the failure to recognize the increasing nonlinearity of the positive relationship between TPR and PP as the base rate departs from the 50% indifference level. This is why we talk about a prior indifference fallacy. If the base rate is truly 50%, if we really have no idea whatsoever whether the hypothesis we are considering is true or false, then there is nothing wrong in concluding that the probability of the hypothesis given the evidence is very close to the probability of the evidence given the hypothesis. But in most cases, it's not true. In most cases, we do have an idea of the base rate, but we don't see it because we're blinded by evidence. If the base rate differs from 50%, prior indifference is a mistake, which gets larger the further away the true base rate is from the indifference level. This is an amazing phenomenon with huge, important consequences. There is hardly anything more fundamental for us than the relationship between our beliefs and evidence. Think about it. You believe the probability of some hypothesis is very high, while in fact is very low, or vice versa. One thought immediately springs to mind. I would like to bet with you and take the other side. But more on this another time. Thank you for watching.